So now we're going to apply our transformation rules. We talked about all of these rules in depth in the previous video, and if you haven't watched that yet, you really need to go and pay attention to all of the rules because I think this really does do with some good explaining to help you understand, and I've got some really good mnemonic devices to help you remember what's going on. But the main topics are we look at the location, is it inside versus outside? We look at the operation, is it added versus multiplied? And then we look at the sign, is it positive or negative? And all of those three things, those three choices, they give us an indication about what this transformation is going to look like. And the other way I like to write that, all of this information, is in this table or this graphic organizer. So if it's added on the outside, that's a vertical shift. Positive moves up, negative moves down. If it's added and it's on the inside, located in the grouping mechanism with X, then we're going to shift, but X is always going to do the opposite of what it looks like. So remember, horizontal, those numbers are shady numbers. They're like in jail. They're behind the bars, grouped in the bars with X. And then multiplying on the outside A. So if it's bigger than 1, it stretches. If the absolute value is fractional, it shrinks. And then if it's negative, that indicates a flip. Whereas with C, multiplying on the inside, opposite, bigger than 1 is going to shrink, fractional will stretch, and negative, less than 0, means we have a horizontal reflection across the y-axis. So again, I detailed all of this in a much more lengthy, with much lengthier explanation in the previous video. So go back and watch that if you need some help understanding. Now let's jump into some examples. For these next few examples, we're going to describe each transformation. We're going to make sure that we state the parent function, and then we're also going to state how the graph can be obtained from its basic parent graph. In order for us to do this, we're going to use descriptive sentences or phrases. When we state our answer, we need to state the type of transformation, a direction, as well as a quantity. And by that, I mean the transformation will either be a shift, up, down, left, right, or a shrink or stretch vertically, as well as potentially a flip or a reflection over either axis. So we'll always be stating vertically or horizontally, up, down, or left, right. And then a quantity. There'll be some number of units attached to each of these answers. Let's jump into our first example. Our first example is g of x equals x squared minus 6. So very quickly, that squared lets me know that my parent graph is going to be y equals x squared. So the most basic squared graph I can come up with is this parabola opening up with a vertex at the origin. So we know the shape is this U-shaped graph. Then we look at the added value. So the difference between the given function g of x and the parent is the fact that we have this minus 6. So again, we think about our operation and our location. The operation here is addition, and addition or subtraction, that implies a shift. So we know this is shift. And because it is outside, it's not grouped inside parentheses with X. Think about like being in jail with X behind bars. It's not inside with X, it's outside. That lets me know it is vertical. So this is going to be a vertical shift. If we were using the variables we had defined, we would say K equals negative 6. But the answer that we would be looking for, the phrase or the descriptive sentence, would be that it's going to shift vertically, and specifically we're going to say down 6 units. So it's going to shift down 6 units. If we had an ordered pair, an initial ordered pair on the graph, and we wanted to transform that, I would have x, y, I would be subtracting 6 from each of my y values to create my new transformed graph. But the answer here is just that it shifts vertically down 6 units. Let's look at another example. For our second example, we have our given function g of x is the absolute value of x minus 2. So in this situation, when we think about what the parent graph would be, we see those absolute value bars. And the most basic absolute value function is y equals the absolute value of x, which is shaped like a V. All right, so there's my parent graph. Now we have this additional value, this minus 2 here. So how does that change the parent graph into this new graph? What is the transformation that occurs? Again, we want to think about the operation and the location. Because this is added or subtracted, but it's added, we say we have a shift. And because it is inside those bars, we know that this is going to be a horizontal shift. And we just need to remember that a horizontal shift, anything horizontal, it's always going to do the opposite of what it looks like. So we think about that as being a shady little number there. So thinking about the fact that there is a minus inside the standard form, we would say that h is actually equal to positive 2. This is like saying the absolute value of x minus positive 2. All right, so we're going to actually shift horizontally, and that's going to go to the right 2 units. So again, the answer is going to be that we shift right 2 units. So that parent graph, if we were graphing it on our graphing calculator, instead of being centered at the origin, would have shifted right 2 units and would now have this vertex at positive 2, 0. If we wanted to apply this to an ordered pair, say we were given a point on the graph and we needed to transform it, we would say x, we would add 2 to the x, and then our y value would remain the same because we're only affecting x here. So this would be plus 2. Notice that difference, right? So horizontal can be a little bit tricky. You just need to practice to get the hang of it. All right, let's look at another example. For our third example, we're dealing with g of x equals 5 times the cube root of x. First things first, what is the parent graph? The most basic graph we can come up with is just going to be a cube root of x graph, which is shaped like this. So it's kind of like a horizontal snake going through the origin. So we know cube root graphs look like this. So then we look at this new number. We've got this 5 here. What is the operation attaching the 5 to the cube root of x? And you guys would all say, well, you read that, it's multiplication. And multiplication lets us know that we will have a shrink or a stretch or possibly a flip. And the location, because it is outside, that lets us know it is vertical. Okay, so this is a vertical shrink or stretch. And the variable we use to represent what that number is doing is a. So we'll say a equals 5. Now, how would we write this as an answer? Well, we would say it's going to stretch vertically by a factor of 5. How did I know it was going to stretch? Since we're multiplying by 5 and 5 is bigger than 1, if you multiply by 5, something gets bigger generally. So we say stretch. And because it is outside, because it's vertical, we know we can trust that it's going to behave properly. So the answer would be that it stretches vertically by a factor of 5. Now there is no flip here because this A value is not negative. So remember, there's no flip, and you don't need to say that. I'm just trying to emphasize that there's no reflection over the x-axis. There's no vertical flip. And if we had an ordered pair, essentially all we would need to do would take that xy ordered pair, we would take the y value and multiply it by A, that positive 5. So this is an example of a vertical stretch. All right, moving on to example 4. For our fourth example, we'll start with g of x equals the quantity negative 2x to the third power. So our most basic parent graph is y equals x cubed. A cubic graph is shaped like this, a vertical snake. So now we're going to focus on the location and the operation. Based off of the parent, we have this additional number, this times negative 2. First off, where is it located? It is inside the grouping, so that lets me know this is going to be horizontal. Remember, horizontal, naughty, bad, in the bars, in jail, does the opposite of what we think. All right, and then the operation. So the operation we're dealing with here is multiplication. Multiplication lets me know it's either going to be a shrink or a stretch, and then possibly we could have a flip or reflection. So this is going to be a horizontal shrink or stretch. Now the variable we use to represent that, we would say that C equals negative 2. All right, now because it's negative, we're multiplying by a negative, we automatically know there's going to be a reflection. So there's going to be a horizontal reflection. If you reflect horizontally, you're going to go across the y-axis. Okay, so we know there's going to be a horizontal reflection. Multiplying by 2, thinking about the absolute value of this. So just the fact that we have 2 here. Well, you'd think multiplying by 2 should make something larger. But because it's inside, it's horizontal, it's going to do the opposite. So we know this is going to shrink by a factor of that reciprocal of 2, which would be 1/2. So the way we'd write our answer is we're going to say it shrinks horizontally by a factor of 1/2. So the negative isn't part of the shrinking. The negative tells us that it reflects across the y-axis. We have a horizontal reflection. So this is the answer we would be looking for. If we were treating that as an ordered pair, my x value would actually be divided by negative 2. So it's shrinking. We have that inverse relationship. And then the y value would stay the same. And you can check this on your graphing calculator. If you plug the parent graph in and this g of x graph in, you're going to get a graph that is reflected across the y-axis, looks like this. Okay, so there's just the plain reflection, but shrinking it horizontally, it's actually going to look like it is steeper. So this graph that I'm now sketching over here in red, that might be what you would see in comparison to the parent. I do want to emphasize that is not a vertical stretch. That is a horizontal shrink. We would be cutting each of the x values in half and then negating them. All right, let's look at a fifth example. For this example, we're given the function g of x equals -1/2 times the square root of x. Thinking about our parent function, the parent function, the most basic square root graph we could come up with, looks like this. All right, so we know we have this square root graph, kind of half of a sideways parabola. And then we, again, think about location. In this case, we are located on the outside, which lets us know this is going to be vertical. And then the operation is multiplication, which lets us know it is either a shrink or a stretch, or potentially a vertical flip. So the letter that we use to represent this extra 1/2 we have here, we're going to say A equals -1/2. So the way we'd write our answer is we know we're going to shrink vertically. So we're going to say shrink vertically by a factor of 1/2. Multiplying by 1/2 is, dividing something in half, and that essentially is making something smaller. So we know we're shrinking, we know we're doing exactly what we expect because this is on the outside. And then all that negative does, this negative here, that lets us know that we will have a reflection. So we're going to reflect vertically across the x-axis, right? Because a vertical reflection would go down across the x-axis. So you're going to shrink by a factor of 1/2 vertically, and then you're going to reflect down across the x-axis. So if you were to look at graphing this in comparison to the parent, so I'll regraph that parent here. Here's my parent graph. You would first see it shrink vertically, so it would be half as high, but then it would also be below, it would reflect down and be below the x-axis. So it'd be vertically smushed, like think about squishing a peanut butter and jelly sandwich, putting your hands down it, smushing it down flat, and then reflecting it across that x-axis. Again, you can always pull out your graphing calculator and look at the picture. The idea, though, is we want to kind of understand these transformations well, because they carry through into all of our future math classes, this concept. All right, so I'm going to just do one more example. For our last example here, we have that g of x equals 1/3x. Now, the parent here would be a rational graph, which is just y equals 1/x. And rational graphs, we haven't talked about those a lot, but they have this kind of hyperbolic behavior. All right, so this is our most basic rational function graph that we can determine. So we have this 3, and this 3 is added on. Now, again, it doesn't go away. We're always thinking about the operation and the location. In this situation, the operation, this is multiplication. And multiplication lets me know I'm going to have a shrink or a stretch or a flip. Now, the location, where is that 3 located? Is it outside or is it multiplied inside the denominator with x? And this is actually an inside situation, which lets us know this is going to be some sort of horizontal shrink or stretch or flip. And remember, when we are dealing with horizontal, we know it's going to behave the opposite of the way we expect. In this situation, we use the letter C to represent something that's multiplied on the inside. C is 3. Now, if you'd think multiplying by 3, normally you'd think times 3 gets bigger. But remember, we do the opposite. So we treat this like division, and dividing by 3 or multiplying by the reciprocal, 1/3, 1/3 of something is actually less. So this is going to shrink horizontally by a factor of 1/3. And of course, there's no flip here. There's no reflection across the y-axis. There's no horizontal reflection because we do not have a negative value. This value that we're multiplying by is positive. Right? So the only thing you would need to answer here would be that it is shrinking horizontally by a factor of 1/3. So in closing here, we have looked at 6 basic one number value transformations and written out the answer of what that physical transformation is, always giving the type of transformation, the direction, and the quantity. And the one thing you may have noticed is there was only one number added in these. So we did 6 examples with just one single transformation. In the next video, we're going to look at multiple transformations all occurring at the same time. So we'll have lots of numbers and we'll need to pick and choose what each one does. As always, feel free to reach out with any questions or concerns. You guys have a great day.